Atlas V is an active expendable launch system in the Atlas rocket family. Atlas V was formerly operated by Lockheed Martin, and is now operated by the Lockheed Martin-Boeing joint venture United Launch Alliance. Each Atlas V rocket uses a Russian-built RD 180 engine burning kerosene and liquid oxygen to power its first stage, and an American-built RL10 engine burning liquid hydrogen and liquid oxygen to power its Centaur upper stage. The RD 180 engines are provided by RD AMROSS, while Aerojet Rocketdyne provides both the RL10 engines and the strap-on boosters used in some configurations. The standard payload fairing sizes are 4 or 5 meters in diameter and of various lengths, and are made by RUAG Space. Fairing sizes as large as 7.2 m in diameter and up to 32.3 meters in length have been considered. The rocket is assembled in Decatur, Alabama, Harlingen, Texas, San Diego, California, and at United Launch Alliance's headquarters near Denver, Colorado. In its more than 4 dozen launches, starting with its maiden launch in August 2002, Atlas V has had a near-perfect success rate. One flight on June 15, 2007, RL10, experienced an upper stage anomaly when the engine in the vehicle's Centaur upper stage shut down 4 seconds early, leaving the payload a pair of naval signals intelligence satellites in a lower than intended orbit. However, the customer, the National Reconnaissance Office, categorized the mission as a success. History: the Atlas V is the newest member of the Atlas family. Compared to the Atlas III vehicle, there are numerous changes. Compared to the Atlas II, it is a near redesign. There was no Atlas IV. The 1.5 staging technique was dropped on the Atlas III, in favor of a more advanced RD 180 engine. The RD 180 features a dual combustion chamber, dual nozzle design, and is fueled by a kerosene liquid oxygen mixture. The main stage diameter increased from 10 feet to 12.5 feet. As with the Atlas III, the different mixture ratio of the engine called for a larger oxygen tank compared to Western engines and stages. The first stage tanks no longer use stainless steel monocoque balloon construction. The tanks are isogrid aluminum and are stable when unpressurized. Use of aluminum, with a higher thermal conductivity than stainless steel, requires insulation for the liquid oxygen. The tanks are covered in a polyurethane-based layer. Accommodation points for parallel stages, both smaller solids and identical liquids, are built into first-stage structures. The Atlas V was developed by Lockheed Martin Commercial Launch Services as part of the U.S. Air Force Evolved Expendable Launch Vehicle program and made its inaugural flight on August 21, 2002. The vehicle operates out of Space Launch Complex 41 at Cape Canaveral Air Force Station and Space Launch Complex 3E at Vandenberg Air Force Base. Lockheed Martin Commercial Launch Services continues to market the Atlas V to commercial customers worldwide. The Atlas V first stage, the Common Core Booster, is 12.5 feet in diameter and 106.6 feet in length. It is powered by a single Russian RD 180 main engine burning 627,105 pounds of liquid oxygen and RP-1. The booster operates for about 4 minutes, providing about 4 meganewtons of thrust. Thrust can be augmented with up to 5 Aerojet strap-on solid rocket boosters, each providing an additional 1.27 meganewtons of thrust for 94 seconds. The Centaur upper stage uses a pressure-stabilized propellant tank design and cryogenic propellants. The Centaur stage for Atlas V is stretched 5.5 feet relative to the Atlas IIAS Centaur and is powered by either 1 or 2 Aerojet Rocketdyne RL10A4-2 engines, each engine developing a thrust of 99.2 kilonewtons. The inertial navigation unit located on the Centaur provides guidance and navigation for both the Atlas and Centaur, and controls both Atlas and Centaur tank pressures and propellant use. The Centaur engines are capable of multiple in-space starts, making possible insertion into low Earth parking orbit, followed by a coast period and then insertion into GTO. A subsequent third burn following a multi-hour coast can permit direct injection of payloads into geostationary orbit. As of 2006, the Centaur vehicle had the highest proportion of burnable propellant relative to total mass of any modern hydrogen upper stage and hence can deliver substantial payloads to a high-energy state. Many systems on the Atlas V have been the subject of upgrade and enhancement both prior to the first Atlas V flight and since that time. Work on a new fault-tolerant inertial navigation unit started in 2001 to enhance mission reliability for Atlas vehicles by replacing the existing non-redundant navigation and computing equipment with a fault-tolerant unit. The upgraded FTINU first flew in 2006, and in 2010 a follow-on order for more FTINU units was awarded. On February 24, 2012, Atlas V lifted its heaviest payload to date into orbit, a £15,000 military satellite, MUOS-1. 2007 valve anomaly the only anomalous event in the use of the Atlas V launch system occurred on June 15, 2007, when the engine in the Centaur upper stage of an Atlas V shut down early, leaving its payload a pair of NROL-30 ocean surveillance satellites in a lower than intended orbit. The cause of the anomaly was traced to a leaky valve, which allowed fuel to leak during the coast between the first and second burns. The resulting lack of fuel caused the second burn to terminate 4 seconds early. Replacing the valve led to a delay in the next Atlas V launch. Proposed development options Atlas V CTS. From 2006 through at least 2014 ULA made proposals and did some amount of design work for a human-rated version of the Atlas V. Atlas V was selected by NASA in late 2014, in conjunction with the Boeing CST-100 space capsule, to be used for human flight as early as 2017. The work began as early as 2006, by ULA's predecessor company Lockheed Martin. An agreement between Lockheed and Bigelow Aerospace that year was reported that could lead to commercial private trips to low Earth orbit 7. LEO. Beginning in 2010, ULA did design and simulation work to human-rate the Atlas V for carrying passengers. ULA won a 2010 small contract of $6.7 million in the first phase of the NASA Commercial Crew Development Program to develop an emergency detection system for human-rating the Atlas V launch vehicle. As of February 2011, ULA is still finishing up work on its $6.7 million award. In December, ULA carried out a demonstration of its emergency detection system. The company said it received an extension from NASA until April 2011 to enable us to finish critical timing analysis tasks for the fault coverage analysis work. NASA solicited proposals for CCDEV Phase 2 in October 2010, under which ULA made a proposal for funding to finish designing a key safety system for potential commercial crew launches on its Atlas and Delta rocket fleet. While NASA's goal then was to get astronauts to orbit by 2015, ULA President and CEO Michael Gass stated, "I think we need to stretch our goals to have commercial crew service operating by 2014, and committed ULA to meet that schedule if funded." Other than the addition of the emergency detection system, no major changes were expected to the Atlas V rocket, but ground infrastructure modifications were planned. The most likely candidate for the human rating was the 402 configuration, with dual RL10 engines on the Centaur upper stage and no solid rocket boosters. On July 18, 2011, NASA and ULA announced an agreement on the possibility of certifying the Atlas V to NASA's human rating standards. ULA agreed to provide NASA with data on the Atlas V, while NASA would provide ULA with draft human certification requirements. As of July 2011, Bigelow Aerospace was still considering the use of a human-rated Atlas V for carrying spaceflight participants to its private space station. In 2011, Sierra Nevada Corporation picked the Atlas V to be the booster for its still under development Dream Chaser crewed spacecraft. The Dream Chaser is designed to be a crewed vertical takeoff, horizontal landing lifting body spaceplane that will be placed into LEO by an Atlas V, and is a proposed CCDEV Islands crew transport vehicle. However, in late 2014 NASA did not select the Dream Chaser to be one of the 2 vehicles selected under the commercial crew competition. On August 4, 2011, Boeing announced it would use the Atlas V as the initial launch vehicle for its CST-100 crewed spaceship, intended for both NASA-funded trips to the International Space Station, as well as for private trips to the proposed Bigelow Commercial Space Station. As of August 2011, a 3-flight test program had been projected to be completed by 2015, and potentially certify the Atlas V CST-100 combination for human spaceflight operations. The first flight was expected to include an Atlas V rocket integrated with an unpiloted CST-100 capsule, to launch from Cape Canaveral's LC-41 in early 2015 into LEO, with the second flight hoped to be an in-flight launch abort system demonstration in the middle of that year, and the test flight phase expected to culminate with a crewed mission at the end of 2015, carrying 2 Boeing test pilot astronauts into LEO and returning them safely. In August 2012, George Sowers, ULA's Vice President for Human Launch Services, stated that if funded, the first manned flight of the Atlas V could occur by late 2015. Replacement for the RD-180 engine, geopolitical and U.S. political considerations in 2014 led to an effort by ULA to consider the possible replacement of the Russian-supplied RD-180 engine used on the first stage booster of the Atlas V. Formal study contracts were issued in June 2014 to a number of U.S. rocket engine suppliers. The results of those studies have led to decisions by ULA to develop a new launch vehicle to replace the Atlas V and Delta IV existing fleet. The Aerojet R1 rocket engine under development as of 2015, is a backup plan to the successor rocket Vulcan, to re-engine the Atlas V. In addition to the ULA backup plan, Aerojet and a consortium of companies seek license production or rights to the Atlas V to manufacture it using the AR-1 engine in place of the RD-180. Successor, Vulcan the Vulcan rocket is the intended replacement for the Atlas V and Delta IV rockets. In September 2014, ULA announced that it has entered into a partnership with Blue Origin to develop the BE-4LOX methane engine to replace the RD-180 on a new first-stage booster. The engine is already in its 3rd year of development by Blue Origin, and ULA expects the new stage and engine to start flying no earlier than 2019. The Atlas V core is designed around RP-1 fuel and cannot be retrofitted to use a methane-fueled engine, meaning that a new first stage must be developed. 2 of the 2,400 kN thrust BE-4 engines will be used on the new launch vehicle booster. Dynetics and Aerojet Rocketdyne have also offered their AO-1 hydrocarbon-fueled rocket engine as replacement of the RD-180. Atlas VHLV. In 2006, ULA offered an Atlas VHLV option that would use 3 common core booster stages strapped together to lift a 29,400 kg payload to low Earth orbit. ULA stated at the time that 95% of the hardware required for the Atlas HLV has already been flown on the Atlas V single-core vehicles. A 2006 report, prepared by the RAND Corporation for the Office of the Secretary of Defense, stated that Lockheed Martin had decided not to develop an Atlas V heavy-lift vehicle. The report recommended for the Air Force and the National Reconnaissance Office to determine the necessity of an EELV heavy-lift variant, including development of an Atlas V Heavy, and to resolve the RD-180 issue, including co-production, stockpile, or U.S. development of an RD-180 replacement. The lifting capability of the Atlas VHLV was to be roughly equivalent to the Delta IV Heavy. The latter utilizes RS-68 engines developed and produced domestically by Aerojet Rocketdyne. As of March 2010, ULA stated that the Atlas VHLV configuration could be available to customers 30 months from the date of order. In March 2015, United Launch Alliance CEO Tory Bruno confirmed on Twitter that the Atlas VHLV will not be developed, instead they would be focusing on the next General Launch System. Atlas Phase 2, with the merger of Boeing and Lockheed Martin space operations into United Launch Alliance in the mid-2000s, the Atlas V program became able to share the tooling and processes for 5-meter diameter stages used on Delta IV. This led to a concept being put forth to combine Delta IV production processes into a new Atlas design, the Atlas Phase 2. If the first stage were to be 5 meters in diameter, such a stage could accept dual RD-180 engines. The conceptual heavy-lift vehicle was known as Atlas Phase 2 or Penthouse 2. an Atlas V PH-2 Heavy along with shuttle-derived, Ares V and Ares V Light, was considered as a theoretically possible heavy lifter for use in future space missions in the Augustine report. If built, the Atlas Penthouse 2 HLV was projected to be able to launch a payload mass of approximately 70 metric tons into an orbit of 28.5-degree inclination. None of the Atlas V Phase 2 proposals reached development. GX rocket. The Atlas V Common Core booster was to have been used as the first stage of the joint US-Japanese GX rocket, which was scheduled to make its maiden flight in 2012. GX launches would have been from the Atlas V launch complex at Vandenberg AFB, SLC-3E. In December 2009, the Japanese government decided to cancel the GX project. Cost. In 2013, the cost for an Atlas V541 launch to GTO was about $223 million. In 2014 the ESA contracted ULA to launch the solar orbiter for around $173 million. In 2015, ULA stated that a low-end Atlas V sells for about $164 million. Since around 2005, Atlas V has not been cost-competitive for most commercial launches, where launch costs were about $100 million per satellite to GTO in 2013. Variants. Each Atlas V booster configuration has a 3-digit designation that indicates the features of that configuration. The first digit shows the diameter of the payload fairing, and always has a value of 4, or 5. The second digit indicates the number of solid rocket boosters attached to the base of the rocket, and can range from 0 through 3 with the 4-meter fairing, and 0 through 5 with the 5-meter fairing. The third digit represents the number of engines on the Centaur stage, either 1, or 2. For example, an Atlas V552 has a 5-meter fairing, 5 solid rocket boosters, and 2 Centaur engines, whereas an Atlas V431 has a 4-meter fairing, 3 solid rocket boosters, and a single Centaur engine. As of 2014, only the single-engine Centaur has been used, with the first launch using the dual-engine Centaur upper stage planned for November 2016, when an Atlas V402 will carry the Sierra Nevada Dream Chaser vehicle for its first orbital test flight. The 4-meter fairing, originally designed for the Atlas II booster, comes in 3 different lengths, the original 9-meter high version, as well as fairings 10 meters and 11 meters high. Lockheed Martin had the 5.4-meter payload fairing for the Atlas V developed and built by RUAG Space in Switzerland. The RUAG fairing uses carbon fiber composite construction, based on flight-proven hardware from the Ariane 5. 3 configurations will be manufactured to support the Atlas V. The short and medium configurations will be used on the Atlas V500 series. The 16-meter long configuration will be used on the Atlas V Heavy. The classic fairing covers only the payload, leaving the Centaur stage exposed to open air. The RUAG fairing encloses the Centaur stage as well as the payload. Versions. As of June 2015, all versions of the Atlas V, its design and production rights, and intellectual property rights are owned by ULA and Lockheed Martin. List date, October 8, 2015. Mass to LEO numbers are at an inclination of 28.5 degrees. Atlas V launches. List date, October 8, 2015. For planned launches, see List of Atlas launches. Photo gallery. See also, comparable rockets, Angra, Ariane 5, Chang'e 5, Delta IV, Falcon 9, GSLV-MK, HIIA, HIIB, Proton, Zenit, comparison of orbital launchers families, comparison of orbital launch systems. References. External links, ULA Atlas 5 data sheets, Atlas 500 series Cutaway, Atlas 400 series Cutaway. Lockheed Martin, Atlas Launch Vehicles, Encyclopedia Astronautica, Atlas V Space Launch Report, Atlas 5 Datasheet.